Hello everyone, I'm Norman Wildberger. In this lecture we're going to be looking at how to compute determinants, and we're going to rely a lot on row reduction and knowing how each step of a row reduction affects a corresponding determinant. But maybe a good place to start is to just have a look at the 3x3 case. Okay, it's a special case, but it's actually quite important in applications. So let me remind you that if you have a general 3x3 matrix like this with entries A, I, J, then the determinant is a sum of 6 different terms. Each of these terms corresponds to a product of entries, one in each row and one in each column, and there are plus and minus signs depending on the sign of the corresponding permutation. Now sometimes it's a little bit challenging to remember that, so I just want to first start by outlining a kind of a quick and easy way of remembering this in the 3x3 case. Okay, the idea is to just copy the matrix down here in blue on the left and then another copy on the right. And then it turns out that the various 6 terms correspond to sort of taking diagonals in this setup. So for example, if we take, say, this diagonal, A1, A2, 2, A3, 3, that corresponds to this term. If we take A1, 2 times A2, 3 and then keep going down here to A3, 1, that corresponds to this term. And then if we go A31, A21, A32, that corresponds to this term. So we're getting all the positive terms with these diagonals going down to the right. Now if we kept on going, to A11, A22, A33, well then we'd just be back to where we started, so there'd be nothing new. So there's really only 3 independent diagonals of this bigger augmented matrix in this direction. Now what about the other direction? Well, if we want to go in the other direction, we could start here. Say A1, 1, A2, 3, A3, 2. Well, that's exactly this term that appears with a minus sign. Put it in green. And then over 1, A1, 2, A2, 1, A3, 3. A1, 2, A2, 1, A3, 3. That's that one there. And then over 1 again. A1, 3, A2, 2, A3, 1. Over there corresponds to that term. So here are the 3 ones that occur with minus signs. So that's one way of remembering how to compute a 3x3. Another important kind of thing to know is that our basic formula, our defining formula for the determinant, actually has some variance. So recall that originally this determinant up here, the determinant, was defined as A11 times capital A11, representing that 2x2 sub matrix, the minor, and then minus A12, A12, and then plus A13, A13. So we're going across the first row here and multiplying each one of these entries along that first row by a corresponding minor of another 2x2 determinant obtained by removing the row and column with alternating plus, minus, and plus for the coefficients. Now, it turns out there's a corresponding formula, in fact, for any row and any column. So this generalizes to a formula involving expansion around any row or, in fact, column. And to figure out what the signs are, you just have to remember this checkerboard pattern. Just like a checkerboard has white and black squares, so we alternate plus and minus signs along this determinant. And this is the 3x3 story, but in fact it works for a general n by n. Okay, so works for the n by n case just as well. But let me illustrate it here. So the same determinant that we were calculating before. Okay, we started off with a matrix A. Let's call this is matrix A. So this determinant A, we had one formula for it here. Here's another formula which is very similar, okay? So suppose we decide instead to go along this row. So we could write it as A, the first element in that row is A21. and then the corresponding matrix, which is a minor A21. And then the next entry along that row would be A22. And we'd have to multiply that by A22. And then plus A23 times A23. So for example, the first term here would correspond to taking the entry here and multiplying it by the determinant of the matrix you get by taking the rows and columns not involving that thing. So that little 2 by 2 matrix there in red, that's the A21 that's appearing here. Okay. So you could go across that second row, get a very similar formula to the one that we originally started with, but it's more flexible. And if we wanted to go down a column, we could do the same kind of thing. So let's say we go down this last column here. So that would be then, the first entry would be A13. That's that entry right there. And we have to multiply by its corresponding minor, A13. And there's a plus sign because there's a plus sign on that checkerboard in that position. And then below it, the A23 entry gets a minus sign and the associated minor A23. And then that's that one there. And then finally A33 times its associated minor A33. So let me give you an application of this formula, which is sometimes nice to remember. So an application is to the cross product of vectors. Go back to our vectors section. Remember that we had the cross product of two vectors. So maybe we have the vector 1, 3, 2, and we want to take the cross product of -2, 1, 4. Okay, we want to know what that is. So there was a formula there, but it turns out the formula can also be remembered with a determinant point of view. Okay, so to do that, let me introduce the standard basis vectors. Say I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. This is often used in engineering courses. Okay, just the three basis vectors. Then we can define this cross product, so this thing here, is equal to, it's a kind of a funny formula. It's a determinant I, j, k, we'll put down the first column, and then the first vector, 1, 3, 2, down that next column, and the next vector, -2, 1, 4, down the third column. Now, what do we mean by this? Well, it's just like we're expanding this, okay? There's I, j's, and k's involved, and the I, j's, and k's are just to be interpreted as these particular vectors. So let me show you how this works. And the key is to expand this out using the first column. Okay? So I remind you that the signs here are plus, minus, and plus. So if I expand this out, I would get I times the corresponding determinant. I'm just going to write that determinant out. 3, 1, 2, 4, okay? And then minus j times the corresponding determinant that you get by eliminating that row and column. There'll be a 1, a -2, a 2, and a 4. And then plus k times the determinant 1, -2, 3, 1. Okay, and what are these things? Well, the first one is 12 minus 2, so that's 10i. And the next one is -4 minus 4, that's 8. So altogether 8, so -8j. And then the last one, 1 minus -6, so that's +7. So +7k. Now, that's a linear combination of the basis vectors. And that's then a vector, 10 minus 8, 7. That's just another way of doing the cross product. And we could check that the dot product between that cross product and any of the two original vectors is 0. So we take the dot product with this one, we get 10 minus 24 plus 14, which is 0. So those things are perpendicular. If we take the dot product with this one, we get -20 minus 8 plus 28, which is also 0. So we've done that correctly. Okay, that's the cross product. Okay, great. Now let's talk about computing determinants more generally. So the most efficient way of computing determinants in general is to use row reduction. Use row reduction. And the key point is there that each of the three basic row operations corresponds to a very specific effect on determinants. If we interchange two rows or swap two rows, the determinant is changed by -1. If we add a multiple of one row to another, the determinant is not changed. And if we multiply a row by a scalar, say lambda, then the determinant is correspondingly multiplied by lambda. So the idea is that we row reduce until we get into row echelon form, and then the determinant is very easy to read. We just look at the product of the diagonal elements. But we have to adjust that final determinant by considering, how many swaps we've done and how many multiplications of rows we have done. So we have to compensate for those operations in the row reduction. Let's have a look at an example. Okay, so let's have a look at this example. Here's a 4x4 matrix, and we want to find its determinant. Okay, so let's row reduce this thing and see what we get. So first step, well, maybe we should start with the actual matrix. So we want to know what this is. Okay, so we're going to row reduce. Okay, so I will copy it 1, 4, 1, -3, 2, 10, 0, 1, 0, 0, 2, 2, 0, 0, -2, 1. And we're going to perform row operations. Our first operation is we're going to take that top one and we're going to subtract twice it from the second row. So the new row 2 is the old row 2 -2 row 1. Okay, and that's 1, 4, 1, -3. And then, so 2 minus 2 is 0, 10 minus 8 is 2, 0 minus 2 is, 0 minus 2 is -2, 1 minus, plus 1 minus 2 times -3 is, I guess, +7. Okay, and then we have 0, 0, 2, 2, and this 0, 0, -2, 1 still stays where it is. Okay, now we're going to do another thing. This one here is fine. It already has zeros below it. So we'll move to this one. And we'll take row 4 will be row 4 plus row 3. Okay, so that becomes 1, 4, 1, -3, 0, 2, -2, 7, 0, 0, 2, 2. And we just add this row. So we get 0 and 3. So now it's in row echelon form, and we see the leading entries are all down the diagonal. Okay, so the determinant here is equal to the product of the diagonal entries. So it's the determinant is equal to 1 times 2 times 2 times 3, which is 12. So now the steps that we performed were all of the kind adding a multiple of one row to another. And crucially, that operation does not change the determinant. So the determinant of this thing was also equal to 12, and the determinant of this thing was also equal to 12. That's what we originally wanted to calculate. So this thing is, in fact, 12. Now, I just want to point out that this is a kind of a interesting little situation where the matrix actually can kind of be subdivided here, and there's a block of zeros in the bottom. And here, this 2 by 2 matrix, it has determinant equal to 2 minus -4, so that's 6. And this one here, this has determinant, this little 2 by 2 has determinant 10 minus 4 times 2 is 8, so that's 2. Okay, determinant is equal to 2. Determinant is equal to 2, and happily the product of these determinants is equal to 12. So there's actually more magic in the world of determinants. So we've only really just touched things. There are classical, beautiful formulas going back to the 18th and 19th century mathematicians who investigated this topic at great length. So there's formulas from Lagrange and Cauchy and various other people. Okay, but anyway, so that's an easy example of how we row reduce. We get to a row echelon matrix, and then we take the product of the diagonal entries and adjust it correspondingly for any swaps that we may have done in any multiplications of rows. Let's do another example. All right, so here's another example that's kind of interesting. It's an important theoretical result that also we've met in the context of fitting a curve to some points. So it's a Vandermonde determinant. And I'll do the general 3x3 case. So it's a matrix which has a very special form that all the entries along every row are just subsequent powers of a single number. So let's say the first row is 1a and a squared, and the next row is 1b and b squared, and the third row is 1c and c squared. So now we have a matrix not with number entries but with variable entries, and that's interesting too, often very interesting, especially in this case. So we want to know what the determinant of this thing is. Okay, so let's do row reduction, but in this sort of general algebraic context. So we'll start by row 2 is equal to row 2 minus row 1, and also row 3 is row 3 minus row 1. So we're using this 1 here to get rid of the 1's below it. We get 1a squared, 0, b minus a here, and b squared minus a squared here. And here, 0, c minus a, and c squared minus a squared. Okay, so how are we going to simplify this? Let's do the following. Let's take row 2, and we're going to divide it by b minus a. And our row 3 is 1 over c minus a times row 3, because we see there's a common factors in the second row of b minus a. Okay, so when we do that, well, we get just 1 here and b plus a. And when we do it to the third row, we divide by c minus a, we get 1 here and c plus a. Now let's take this entry here and use it to get rid of this entry here. So the row 3 will be row 3 minus row 2 for a total of 1 a squared, 0, 1 b plus a, and 0, we get 1 minus 1 is 0, and c plus a minus b plus a is c minus b. Okay, so now we're in a row echelon form. We see that the entries are along the diagonal here, and we can read off the determinant very quickly. So here the determinant is equal to 1 times c minus b. So it's c minus b. So what about here? So to go from here to here, we added a multiple of one row to another. That doesn't change the determinant. So this determinant is also equal to c minus b. But what did we do when we went from here to here? What we did is we divided by b minus a, one of the rows, and we divided by c minus a. So we have to compensate for that. Okay, that means the determinant here is going to be c minus b that we already have times b minus a times c minus a. And the first step that we took was adding a multiple of one row to another. We know that doesn't change the determinant. So this last thing here that we get there is also the determinant of this thing. And so we can conclude that the determinant is, therefore the determinant of, let's say the matrix A, let's give it a name, so that's A. It's equal to C minus B times B minus A times C minus A. It's a product of the differences between the three entries A, B, and C. So in particular, if A, B, and C are distinct, so if A, B, and C are distinct, that no two of them are equal, then determinant of A does not equal 0, and so A is invertible. And it might be a fun little exercise for you to calculate what the inverse is in this case. Okay, so these are some of the kind of important things. Maybe I will just mention a few more things sort of to finish off things. So I remind you of the main theorem that I told you about last time, which I didn't really prove at all. It actually involves a little bit of work. But actually, okay, basically a proof of this multiplicative property of the determinant involves examining, again, the consequences of multiplying by elementary row matrices. Well, you could do that, but it's maybe another 10 minutes. So I'm not going to actually prove that. But it is an important result, and it has some consequences which are also useful when you're calculating things. Okay, so another consequence is the following proposition, that if A is an n by n invertible matrix, then the determinant of A inverse equals 1 over the determinant of A. That's a very nice thing. The inverse matrix has the inverse determinant. And the proof is pretty simple. It's simply a consequence of the fact that since A times A inverse equals the identity matrix, we know that the determinant of A inverse, which is the determinant of the identity matrix, which is 1, equals the determinant of A times the determinant of A inverse. And that's basically what we're saying. We're saying the determinant of A times the determinant of A inverse is equal to 1. Okay, so that's probably a good place to finish. So we've outlined some kind of key techniques for computing determinants. There's a lot more to be said about determinants. It's a very classical and rich subject that was extensively studied in the 19th centuries and earlier too. In fact, it actually came before sort of modern linear algebra. But it's still of a theoretical importance. But these days, our computers are very good at calculating determinants. And usually, determinants are calculated by computers. That's just the reality.